Hello, everyone, and welcome to Season 3, Episode 3 of the Wolfram Student Podcast. I'm Tiani, and I'm your host. This is the Wolfram Student Podcast, where each episode we dive into a new innovative project done by high schoolers or undergraduates using the Wolfram language. For this episode, let's welcome Sindhoora, who will be discussing her project analyzing polysaccharide bonding in Cryptococcus neoformans. Hi, Sindhoora.
Hello, I'm Sindhoora and I'm from India. I'm in 11th grade and I go to a national public school.
Great, thank you so much. And to begin with, could you just tell us briefly like what your experience with Wolfram is, what camps you've gone to?
I started off with WSRP 24 and then I just completed WELP. And yeah, I have done TA training as well.
That's really exciting. Yeah. I really enjoyed WSRP and I also did WELP. And I also went through TA training and that was a really fun experience. And just a classic question that we like to ask people when they come onto the podcast is like what's your favorite Wolfram function and why?
Well, if I had to choose one, it would be the molecule value function. And honestly, I feel like it's 20 to 30 functions compressed into one. It can do a lot of things that, yeah, you may not probably be aware of.
Yes, yeah, I think that for sure makes sense. One of the really cool things is how versatile a lot of the functions are. Great. To begin with, could you give a brief summary just of what your project is about and what we're looking at?
So, Cryptococcus neoformans is this really opportunistic fungal pathogen that poses a threat to immunocompromised individuals worldwide. And what makes this organism particularly fascinating from a molecular perspective is its really complex polysaccharide capsule, which serves as its primary virulence determinant. And this capsule forms a protective barrier around the fungal cell and shields it from host immune responses. And this is particularly useful for the fungus in immune evasion and poses like significant challenges in case of treatment. So, the research project is focused on the fundamental building blocks of this capsule. So, we're looking at the monosaccharides that make up the polysaccharide capsule that include glucuronic acid, mannose, and xylose. So, using like computational modeling and potential energy surface exploration, the preferred conformers of these molecules are determined, and we look at how they exactly look at their stability and how they really form the complex capsule structure that enables Cryptococcus neoformans to evade host defenses.
Great. Thank you. And just for people who might not be familiar, what are like monosaccharides or saccharides? Are they just sugars?
Well, they're just sugars. A polysaccharide consists of multiple sugar molecules, and these individual units are called monosaccharides.
Okay, great. Thank you so much. This sounds super, super interesting. So let's get into it.
This is the brief abstract that we have here. We look at the first monosaccharide, that's glucuronic acid, and this is one of the most critical components of the Cryptococcus neoformans capsule. And glucuronic acid is a uronic acid derivative structure, and it introduces really unique electronic effects and hydrogen bonding capabilities. So over here we're just using molecule modify. We're computing the atom coordinates and basically generating the molecule, and then here's the 3D plot of glucuronic acid. And yeah, this is a 2D plot with indices which are used later on. We're using, so these are the torsion angle rotations. So as you can see over here, this is basically a manipulate function. And this is an image of a manipulate function. And when these bars are manipulated, you can basically see these dihedral angles, these torsion angles in the hydroxyl groups really moving around. And the moving around of these torsion angles basically contributes to different energy levels, and the energy levels change as these torsion angles are manipulated. And at the lowest, and we're looking to find the lowest energy conformer where the configuration of these torsion angles hits the minimum energy point, and we're like visualizing this later on, so I'll get back to that.
And
So
just
first of all,
really quickly, a quick question. So in terms of how like the conformation of the molecule relates to the energy, like what exactly is that telling us? So for example, like are we looking for the lowest energy conformation because that's the one that's most likely to like to show up and appear in nature? Or like in what would a higher energy mean for like a certain conformation?
well, as you mentioned, a higher energy would indicate like a really unstable molecule, while a lower energy would indicate a really, really stable molecule. And the lower the energy, the more likely it is to be found in nature, as you mentioned. So that's why we're looking at these low energy conformers specifically.
I see. Okay. And then I'm just wondering, is like the way that the energy is calculated like in one of the functions, or like how do you know how the energy is calculated for like a certain conformation? Is it just based off of like the interactions between the hydroxyl
Yeah,
group?
so the energy, the primary energy field that's used over here is called the Merck Molecular Force Fields, and this force field is really versatile and reliable in particularly modeling organic compounds with it has a really wide range of applications. So this is I mean, if you look at the pyramid all the way up top, you have the Schrodinger's equation, and yeah, and that would take a really, really long time to compute. But all the way at the bottom of the pyramid, you have the Merck molecular force field. So that's pretty easy to compute in computationally, especially. And yeah, that's why that was used. So all the way up top, we have the Schrodinger's equation, and this is like a baseline of it.
I see. Okay, that makes sense.
So over here we generate 700 conformers. So conformers are basically these molecules that have different torsion angles compared to each other. So these are basically isomers in some form, and 700 of them were computed, and I did try to compute more, but unfortunately my Wolfram language, the system kind of crashed.
Hmm.
So yeah, so these are 700 conformers put together in one plot, and these are the this is basically the histogram of the Merck molecular force field and the number of conformers computed. So these conformers would be the most stable, while these ones with a really high Merck molecular force field would be really unstable.
Hmm.
So the problem that we encounter over here is that there might be a switching of bonds. So right here we have bonds that are, I mean, if you look at these three atoms, they need to be in some kind of relationship with the entire molecule, and sometimes that relationship is not maintained. So there's some geometric like calculations that's done. So over here it doesn't really look geometrically accurate, and you can see that there is the atoms are not in proper relation with that with the molecule as a whole. So that's why we run through some geometric calculations to make sure that it falls within a really particular range. And yeah, so we go on and then we filter these molecules. We filter to find the number of appropriate conformers, and uh, and then we plot and then we calculate, I mean, we derive the minimum energy molecule from the number of conformers that are geometrically right. And this was the one that was found. So this was the minimum energy molecule of glucuronic acid.
Mhm.
And after that, we plot, as I mentioned previously, we look at the energy, we plot the energies with respect to movement and torsion angle. So this is the torsion angle movement of one hydroxyl group. And yeah, so if you look at the graph, you'd see at these particular points, it's relatively stable compared to the instability right over here. So we take the minimum energy point of this conformer, of this particular conformer, and then we take that to be the least lowest energy variant of that a group of that hydroxyl group, if that makes sense. And we do this for all the three hydroxyl groups that, all the four hydroxyl groups that are present. And then this is the carboxyl group. We do that for that as well. And over here you would see a unique variant, and then it's pretty clear that this is the point of the lowest energy, the minima basically. and and we this is the whole methodology of analyzing one particular molecule, and we apply this to all the other molecules of the glucuronic acid capsule, that's mannose and xylose. So these
Uh,
are the
so,
other
sorry.
two compounds.
So above for the plot that yeah, for these plots, so it's really interesting. It looks like at least for the hydroxyl groups, the lowest like molecular energy is found like when the torsion angle, like the magnitude of the torsion angle is really, really high. So between choosing whether it's like turned negative 150 degrees or 150 degrees, did you just pick whichever one is lower? And does the direction that you pick matter when you're choosing the other ones? So for example, if for the third hydroxyl group, it looks like turning negative 150 is lower, does that affect like which if you go negative 150 or 150 for like for example the fourth hydroxyl group? Or did you just pick like the lowest for all of those?
Well, we pick the lowest according to what's possible. So we generate these conformers, right?
Mm.
So it's some of these are not really geometrically accurate, and at the minima, if the configuration of the torsion angle is geometrically accurate, we pick that. So when we rotate this torsion angle from minus 180 degrees to 180 degrees, what we're basically doing is rotating it a whole 360 degrees. We just have to ensure that there are no geometrical irregularities, in the sense that the atoms are right in respect to the entire molecule. So if that condition is met, we pick the lowest energy minima of these torsion angles, despite if we're going negative 150 or 150. We just have to ensure it's geometrically accurate.
Interesting. Okay. And then when you're rotating each of these, like I'm guessing the rest of the molecule and like the rest of the hydroxyl groups are like being held in the same position. And you
Yep,
just
that's
rotate.
right.
Yeah. Okay. I
Yeah,
see.
we're only rotating that particular functional group.
Interesting. Okay.
So the same methodology is applied for mannose and xylose as well. So this is mannose. It has kind of a similar structure to glucuronic acid, except for this functional group. So yeah, so this is mannose, the molecule, and then in this animation you can see that this particular functional group is being rotated. Yeah, so this is basically how it happens visually, while all the other hydroxyl groups are kind of stable.
I see.
And so further, we generate 700 conformers for this as well, and this is how it looks when plotted together. It's a really, really dense plot, and this is the histogram again. And yeah, so we look at geometrical optimization here as well. And yeah, so we filter it and then we determine the lowest energy minima for these filter molecules, and this is the minimum energy molecule for mannose. And yeah, so what's interesting is for mannose as well as glucuronic acid over here, it has these tails that are kind of leading to each other. And so the broader scope of the study was in collaboration with Johns Hopkins University and Wolfram Research. So this was a part of it. So these structures were computationally proved over here, and these were the same structures that were used by the people at Johns Hopkins for
Mm.
their experiment. So this was a computational proof of this. And yeah, so coming to these plots over here, this is the torsion angle plots, and you can see how it variates with the rotation by of 360 degrees, and then we take these minima, and after that we move on to xylose. And yeah, this is xylose, so this is the structure of xylose. And we go ahead with the same process of here. I think you can see this a little more clearly. So this is the rotation that's happening. And yeah, so it kind of flips out because of the 3D area over here. And yeah, you can see that pretty clearly. So we
Okay, so
generate 700 conformers. Yeah.
yeah, I'm just trying to look at the like rotation, um, and see exactly what is happening. So is the one that is being rotated the one that's like in the beginning on the right over there?
Yeah, that's right. This one. I think, yeah, that one's being rotated, if you can
Okay.
see.
Yes. And then I was just wondering because I can see it's being rotated like in this portion right here, and then it looks like when it reaches a certain angle, the like entire molecule flips. Is that just like how it's displaying it? Um,
Well, that's a limitation, I would say, because yeah, so earlier before we ran some optimizations and the manipulated was flipping up pretty badly. So we're trying to fix this fix the like torsion angle to this point while the molecule is kind of rotating. So I think that's what you're seeing when you flip. So although this torsion angle kind of remains at that particular place, the molecule kind of flips. So that's kind of a limitation right now.
I see. I see. Okay.
And we do the same process for xylose. And yeah, we run geometric optimization again to ensure these two atoms are right in respect to these other in respect to the molecule as a whole. And yeah, so we then further compute the minimum energy molecule, and then this is the molecule that's given to us, that's proven computationally, and these are the graphs again. And further you have further I mean, like, you may ask, what's the whole point of doing this? What's the whole point of this experiment? So basically, Cryptococcus neoformans, the original fungus, actually kills over 180,000 people worldwide. And it's a pretty large number for fungus. So, and there are not really effective drug targets for this fungus. So basically, by looking at the capsular polysaccharide, that plays a really important role in its defense against the human immune system. We can potentially identify drug targets and specifically identify compounds that could potentially target the capsular polysaccharide, leading to antifungal agents. And this is basically Merck Molecular Force Fields, which is a really, really low level calculation. And we could potentially apply sophisticated computational methods like DFT, that's density functional theory, or use molecular dynamic simulations and find out what exactly happens when you put this glucuronic acid molecule in water. So that would be a really realistic simulation of what's exactly going on in our body. And yeah, so higher level quantum mechanical calculations could also serve as benchmarks for method validation. And you could potentially look at the electronic effects influencing conformational preferences. So over here, we're just looking at the conformers and yeah, how they're basically affecting your energy levels. But we're not looking at why exactly that happens. So that would be a potential idea for a future direction. And yeah, so Cryptococcus neoformans is not the only fungus that's covered with a capsule, and various other bacterial pathogens, as well as another fungus called as Cryptococcus gattai, if I'm not wrong, also has this capsule. And yeah, so they have similar structures, and this research could also be applied to those capsules to look at the broad spectrum antifungal strategies or antibacterial strategies, and maybe explain species specific virulence mechanisms. So in conclusion, basically, we are looking at the conformational landscape of glucuronic acid, mannose, and xylose, and these look at fundamental insights into the molecule architecture behind capsule formation in Cryptococcus neoformans, and the energy landscapes reveal these relationships between molecular geometry and stability, and basically they highlight specific conformational preferences that may be really important for polysaccharide assembly and interaction with the host immune systems. And moving forward, I think we could potentially use these conformational data with really experimental studies and more sophisticated computational approaches, and perhaps we could potentially identify novel therapeutic targets for the destroying of the fungal capsule. So I would like to thank Dr. Sonnenberg from the Wolfram chemistry team and Grayson Gerbig from Johns Hopkins School of Public Health, who introduced me to this effort in biochemistry. And I would also like to thank my teaching assistant, Alexander Doe, for his support. So at WSRP, we sat together as as a group, and we really all of the chemistry project students helped each other, and I think that was a really valuable part of it. And WSRP overall was a really valuable experience for future endeavors as well.
Thank you. Thank you so much. That is super interesting. I know Jason and Alexander, and they're both really, really cool people. I just had a couple of questions, kind of regarding like some of the things you said for future directions. So in this project, you're mainly looking at kind of like the monosaccharide components, right? Like you're looking at the conformations of like each of the like saccharides on their own. Given that like Cryptococcus neoformans is like a lot of these saccharides like chained together. I don't know, like do you know or like what do you hypothesize about how like maybe their conformations change when they have to bond with like other molecules? Like is the lowest energy conformation the one that is most conducive to like the bonds being formed with others? Or are there times where like it has to go to a higher energy conformation in order for this to happen?
Well, I believe that I think that the lowest energy conformer is the most stable state found in nature, and you don't really see molecules of a really high energy configuration. So, what we're expecting, what I'm working on is what if you put this glucuronic acid molecule in water? What really happens. I mean, we expect it to go into a lower energy state, so that's what I've been looking to work on. And yeah, so I think the results will be pretty interesting. But yeah, so we're expecting, so the lowest energy conformer is the one that's most commonly found in nature. It doesn't necessarily go to a higher level to interact with other molecules, but stability, I mean, but it'll try its best. The molecule will try its very best to move down to a lower energy state through
I see.
interactions.
I see. And then you mentioned that for some of the like saccharides that you were testing, that they were like in the same conformation as the ones that you found that like other researchers were using. I was wondering like for those conformations, like I'm guessing you also had like what the minimum energy of that molecule was. Were you able to see if like those calculated values that you had matched up also with like calculated values for those conformations from other people? Like not only did the conformations match, but so did the energies.
Yeah, so I don't think the energy levels were calculated at with like from by other researchers,
Mm.
but they used the same configuration of the molecule, if that makes sense. The energy level was not calculated, but if you look at this molecule right over here, this was the same molecule that was used by that was supposedly which they believed was probably the lowest energy conformers used by them in their experiments. So this is basically just a computational proof of that, if that makes sense.
I see. Okay. Yeah, that makes sense. This is really, really interesting. So I guess I'm just wondering, like, it sounds like you have a lot you're thinking about for doing in the future for this project. And I'm wondering if you also have like different projects you have in mind that you could potentially do with Wolfram.
Well, so recently, a group of students and I, under the mentorship of Dr. Sonnenberg again, we worked on this protein analysis system. And yeah, so it basically calculates the occluded surface area and the Monte Carlo surface area of proteins, and that was our WELP project. It was a huge part of our WELP project, and yeah, so that doing that was pretty cool. And yeah, so I've also been looking at, I think since Wolfram 14.1 came out, they've added a whole bunch of things, and with 14.2 even a lot of things were added into the system, added into Mathematica, and it's really interesting. I think the computational bio side has increased, the computational chemistry side as well. It has introduced a lot of new functions, and yeah, I think yeah, I was looking at proteins a while ago. Yeah, and I hope to work with proteins and also look at how glucuronic acid really interacts with water molecules as part of this project, as part of an extension for this project.
Yeah, for sure. I definitely agree. I think like computational biology in general as a field is really, really exciting to think about. So good luck on all of those future projects. And thank you so much for coming on the podcast and sharing.
Thank you so much. It was an amazing experience being here.
Thanks for listening to this episode of the Wolfram Student Podcast. We hope you learned something new and took away insights from today's discussion. If you want to learn more about Wolfram summer programs, research opportunities, or be featured in a future episode, check out the links in the description below. Be sure to tune in to check out our next episode. This is your host, Tiani Gu, and thanks for listening to this episode of the Wolfram Student Podcast.